So what is an antiderivative? That's like when you're not pro-derivative, right? When you're antiderivative. Yeah. Okay, so all of you geniuses who have taken calculus before, obviously you can tell me what an antiderivative is, right, Tulip?
I want to say it's an integral.
Oh, I was
but
hoping someone would say that so I can tell them they're wrong. Okay, so please get this all out of your head. For anyone who's taking calculus, if you think an antiderivative is an integral, you are absolutely 100% wrong, and you need to get that out of your head pronto. So we say f is an antiderivative of f on the interval. There's always an interval that's associated to it. If f prime is equal to f. That's it. So an antiderivative is a backwards derivative, right? So in other words, so you're so used to saying, oh, here's the function little f, give me, and then it's not equal to, and then give me f prime. Well, now we want to go the opposite way. Now we want to go the opposite way. Give me a function big F whose derivative is the function I just gave you, right? Well, now there is a major theorem that we really can't prove in this class because you need what's called the mean value theorem to prove this. The mean value theorem is actually one of the most important theorems of calculus, but for theoretical purposes, but we don't really do it in this class. So mean value theorem can actually be used to prove the following. So one of the big questions is, how do you know you have found all possible antiderivatives of a function? Because obviously there's definitely more than one, right? Because you can always add a constant onto something, right? The antiderivative of cosine of x, for instance, right? What is an antiderivative of cosine of x? Sine of x, right? But I can always add a constant onto this. I can always say +3 or -4 or plus pi, right? I can always add a constant, so I can get infinite many derivatives. So there is no such thing as a unique antiderivative. So it kind of begs the question, well, how do you find them all? Are there any other ones? And it turns out adding this constant is really the only thing that can kind of really happen here. So suppose f and g are both antiderivatives of the same function. On the same interval. Then those two antiderivatives are really not that different. They really just differ by a constant. There's some constant c such that g of x equals f of x plus c for all x in AB. You should appreciate that this theorem is not trivial, right? It's actually equivalent to saying the following. If I told you that the derivative of f was 0, right? And I asked you, what could f possibly be? Obviously, you would tell me f could be a constant, right? But the question is that the only possibility? Are constants the only functions whose derivative is 0, right? I mean, it's very clear that constants have derivative 0. That's trivial. But the question is, are constants the only functions that have a derivative of 0? And that actually turns out not to be a trivial question. It might seem that the answer is obvious. I'm telling you it's not. So to actually prove that constants are the only such functions, you actually do need mean value theorem. And that's really what this theorem is saying. Because you can always just do f minus g, and that derivative is 0. So it is a very important theorem. But it's also very useful because once you found one antiderivative, you found them all, right? So for instance, if I ask you, what is an antiderivative of cosine of x? You tell me, oh, well, sine of x, definitely. Because the derivative of sine of x is cosine of x. And if I want to find them all, I just add any arbitrary constant. Now I found them all. That's it. There's no other antiderivative. Any antiderivative of cosine of x must be sine of x plus some constant. That's it.
Wait, so for tangent x, would it be secant x squared plus c?
No, that's the derivative. The derivative of tangent of x is secant squared.
So
But what is the antiderivative of tangent of x? Well, that will come back to when we do substitution rule. The answer turns out to be ln of secant of x plus c. But we haven't done that yet. Again, antiderivatives are going the other way. You're not doing the derivative rules you already know. You're going backwards. Forgetting that c cost me so many points on high school calculus exams? Probably. Maybe if you understood why the plus c has to be there, you wouldn't have forgotten it, right, Alex? Maybe if your teachers actually taught it to you, because all high school teachers suck. Is that it? No, that's not true. My high school teacher was amazing, but okay, so this is special notation. I mean, obviously we have special notation for derivatives, right? When we talk about derivatives, we either use primes or sometimes we use, the ddx notation. So we have similar notation for antiderivatives. Right? Of course, are you saying RT for retweet or just something else? Like you're retweeting Alex's Zoom chat message? Okay, good. Special notation. So we use this notation. So it's like an elongated S. In fact, actually historically it started out as an S and then over the years it got elongated. So this notation means the most general possible antiderivative, the most general antiderivative of f with respect to x. And the interval is usually understood. Okay, so that's just special notation we use. Your book will call this an indefinite integral, which is really, really bad. So you might see that term thrown around. It's a really, really bad term because it suggests that this is an integral. This is not an integral. An integral is a completely different construct that we won't do until after the last exam. An integral is a limit of Riemann sums, which is meant to represent the area under a curve. An integral is not an antiderivative. They're two entirely different things. So to kind of mix them up, I don't like calling it indefinite integral because I think it kind of, I think it just furthers this misconception that antiderivatives and integrals are the same thing, and they're not. So